In this lecture 8, following the bound structure study, we are going to see how the electron can propagate in a different type of semiconductor materials. So let's start from here by reviewing the bound structure. And as we've already mentioned, the gamma position, and there's some notation in the bound structure diagram. And gamma indicates no directional, no k direction, and x is 1, 0, 0 direction, and L is 1, 1, 1 direction. And as you can see that there are two types of the band gaps and also semiconductors. And the one is that here's the electronic state available for these materials, and this top of the bottom is the conduction band, no, valence band edge, and this bottom of top side is called the conduction band edge. So this conduction band and valence band. And if you can find the light absorption, the electronic state from the top directly to the here, it's called a direct transition. But in the case of silicon like this, the bottom of conduction band is in the X position, so light cannot be directly absorbed. So there's called an indirect band transition with the help of the momentum conservation of the phonon, which is not described here, which is not studied here. But anyway, in the case of indirect band gap semiconductor, the light absorption is much smaller than the direct band gap, which means that from the top of the valence band to the bottom of the conduction band, there's some direct energy levels. The energy levels available for its transition, which is called a direct band gap transition. So, as we talked about, these valence band and conduction band is simplified and drawn like this. And when the light is illuminated, the electron is excited from the valence band to the conduction band, and the charge charge remaining. So the charge of the positive charge due to the electron is excited is called a hole, and which has a positive charge, and electron of course has a negative charge. And we can think about the mobility of charge carriers, and this is described by the physical properties called effective mass. And here's the final result of the effective mass that I would just want to first emphasize. This can be obtained from the bond structure diagram. So what it means, right? So this indicates the second derivative of epsilon with respect to k. So what we could obtain from the bond structure is basically the energy and k drawing, whatever it is complicated. So if you have some structure, you can differentiate twice, and then you can obtain the inverse of the mass of charge carriers. So bound structure directly gives the mass of electron or holes. This is a take-home message at first. And how to obtain this equation is a bit complicated, but please try to follow these and then you can obtain that. So first up, the electron is regarded as a wave, and the energy of electron can be transferred by was a group velocity, not a pure velocity. So the velocity of group velocity is given by differentiation of the omega angular momentum with respect to a wavelength. And then which is equal to 1 over the dk. So just think about in a one-dimensional. And please try this equation to obtain this, but as an exercise. So equation motion of the electrons can be described with momentum of h bar k equal f, and also this can be a conventional equation of motion, ma equal f. So you can compare these equations, and then what you have to obtain is this m. And during this calculation, substitute the second equation to first one, and compare the third one and fourth one, and you can obtain this m value was this equation. So this equation or this bound diagram, actually how much this information, this includes the information that how much charge carriers can move around too. So again, what it means is more important. So in the case of epsilon is proportional to the constant times k squared. So you can take the derivative twice, and then you can obtain the effective mass like this. You can just simply substitute ak squared into the equation. So that means this a value curvature is more important, right? If a is larger, the m is smaller. So a is larger. When the a is larger, that means this curve, right? This curve is steep. In this case, a is larger, and then m is smaller, so easy to move around. But if the curvature is something more shallow, like this, the a is smaller and m is bigger, so meaning the charge cannot move around so much. And the other important point is meaning that the boundary structure is more complicated. So depending on the electron staying at each state or the structure, at each position, actually the effective mass is changing, varied. So depending on which valley the electrons are staying in, so the mass itself is different. So if you check out the mass, effective mass for different materials, for example, here you can find several different values for electron and holes. So this is because what I explained here. So depending on which curvature state your electrons or holes are there, the effective mass, so how easy to move around, is different. Okay. And also there are many different values, meaning the different the electrons in the different state or holes different states.